Hey guys, as promised, here is the tutorial walkthrough for the electric potential problem that we encountered in the tutorial. And I'm going to give you guys a walkthrough, and mainly the reason is to address what happens in part B, where you only get one answer but you should get two. As always, it's good practice to try this on your own, see if you get the right answers, which will be presented at the end, because physics is all about trial and error and practice and repetition. So give that a go. Pause it here, try that, and then when you're done, come and follow me as we go through this. So part A is looking for us to calculate the position when where the electric field is 0 on the x-axis. So to find electric field, what we need to do is we need to place a positive test charge, and I'll just place it here arbitrarily. And for electric field to be 0 is when the force that this particle experiences is 0. And so the forces it's going to experience an attractive force from this negative charge, is going to be pulling it in that direction. And let me draw that actually. So it's going to feel a pull in that direction. And then from the positive charge, it's going to experience a repulsive force, pushing it in that direction. So what we have to do is add up these forces and find out when they equal 0, and that is, at that point, that's when the electric field is going to be 0. And so let us write down the equation for force from point sources. And that equation is going to be simply the force for each one is going to be some constant k times the charge times the test charge all over the radius squared, or the distance between the two squared. So this is the equation we need to use, and we're going to need to use it twice actually, because we have the positive charge pushing it and we have the negative charge pulling it. And so let us write the total force on our charge, and so that total force, I'll just call it total force, is going to be k times the q1, and q1 in this case is the charge of the first point particle, and that's 2 microcoulombs. I'll just put 2 micro there. And then times the charge on the point charge, and the point test charge we're just going to give it a 1. And that's going to be all over a distance, but what distance? So let us define the arbitrary distance where we're going to set this, and we'll call this distance between these two here, we'll call this d. And so that's going to be all over d squared. And now we have the force between the negative and positive test charge, and that is going to be pushing it in the negative, or pulling it in the negative direction, and so that's going to be k times, and since I've already stated it as negative, I'm just going to write the magnitude of the charge here, 5 micro, and times 1 for the positive test charge. This is all over, and then again, so if this distance here is d, then the distance between these two charges is going to be d less 1.6. So let's write that right here. So that's going to be d minus 1.6. So this is going to be all over d minus 1.6 squared. And we know that the electric field is 0 when the force is 0, so we just set that to equal to 0, and now let's solve. So I'm going to skip the gory algebra details and just give you a summary. So now this leaves us with a quadratic that we need to solve in order to get the distance. And then after solving for the quadratic formula, we have the two possibilities for distance. So d could either be negative 2.75, in which case instead of d being this way, d would be negative in this direction, or it could be positive 0.6. So that would be about somewhere in here between these two. Now we have to see if both of these are possible. So if it was negative 2.75, it would put it over here, and that would mean it would be attracted by the negative charge and repulsed by the purple charge. So that could work. However, if it was in the middle, then it would be forced to the right by the positive charge, and it would be pulled to the right by the negative charge. So there's no point at which, in between these two, at which the force could possibly equal 0, because you're adding two forces that are pushing it in the right direction. So therefore, it cannot be 0.6, and it has to be only the distance of negative 2.75. And so that's how we do part A. So now most of you got part A, but here part B has a trick in it that I want to walk you guys through. The first step here in part B is the same as part A, and we just use this formula here for the potential of a point source versus this formula here, which is the electric force formula. So okay, so let's apply this. Again, we're going to do it at some arbitrary point here. We'll just call that a distance d away. And so we're going to do the total v at some arbitrary point d. Actually, let me just highlight this first. So yes, that point there is going to be equal to the potential at from the positive 2 charge, and that's plus the potential from the minus 5 charge. Okay, and we know that these have to equal 0. And what are they? So now we do this formula here, the kq over r. So for the first charge, we're going to have k times the q of 2 micro over, and so here's where the trick comes in. So what you could do with sort of without knowing what you're doing is you just put a d in here, and because that's the distance, right? Obviously, seems to make sense. And then you add the second term here. That's from the minus 5 potential, and so that's going to be k times negative 5 micro all over, and then this distance is d minus 1.6. So now you could just solve for this. If you square both sides, you will get the right answer. But the question is, why? Right? So I can just leave this with you guys, and you move this to the other side, you square both sides, you will get the right answer. But I'm going to show you the intuitive way to get to the right answer. And that is going to require us to know that we are in 3D space here. Okay? So in 3D space, we don't just put the distance, we use a sort of, we use the Pythagorean theorem and get the distance for the x, the y, and the z component of the distance from these charges. And so what is that? So in this case, r would be the square root of the distance from the x squared plus the distance from the particle in the y direction squared plus the distance from the particle in the z direction squared. Using this and this, then we can get to the right answer, and it makes physical sense. So now let's apply this formula again using these two equations. We know that the potential at some point, we'll just say it's the distance d on the x-axis, is going to be 0. And the k, so we don't know k, we'll just put it in there, it's a constant. The charge is positive 2. That is over, and now we do the square root. That's going to be in the x direction, it's d squared. In the y direction, it's 0 because it's on the x-axis, so there is no y component, so it's going to be plus 0 squared. And then in the z-axis, which is up out of the page and into the page, it's also 0. I'll just leave it, so because these zeros are just gonna vanish. So we have that, and then we also add for the negative 5 charge, 5 microcoulombs. And that, again, is going to be the square root. And then we have the x component. And what's the x component? It is the distance in the x direction from our point here to the particle is going to be d minus 1.6 squared, and then plus 0 again. So let's move the second term over and simplify. And each of these have, you can factor out a k and a mu, a micro from both sides, and those will cancel out. So get rid of those. So now, again, we can square both sides, and it brings us to this situation over here where you'll get a quadratic, you'll get the right answer. But if we exploit the taking the square root of both sides, we can get out a plus or minus in front of this guy here. That'll allow us to skip the quadratic and still get the right answer. And this can actually be applied after this step here too, if we take the square root of both sides. And if you do that properly, where you take the square root of both sides, but you make sure you take plus or minus, because that's what you have to do when you do that, then you'll get the right answer. So let's apply that here, and just a little shortcut that if you want to use, great, but if you'd rather just square it and run, then that's fine too. You'll get the right answer. And so what we do here is we assume d could be plus d or minus d when it gets squared. And when we take the square root of the square of the plus or minus, both answers are valid. And so we're going to need both the plus or minus of that. We could have taken the plus or minus of this element inside that's squared as well, but I just took this side. You'll get the same answer. So we take plus or minus the d, and then we bring it over to this side, and so that gives us plus or minus 5d equals, and then 2 times what's in the bracket that I brought up here, d minus 1.6. And so we know that this, you either add 5 or subtract 5, and when you bring the 2 over, then that's going to be add or subtract from minus 2. You work that out, and this is what you get, the right answer. So we do that in about 3 to 4 lines, whereas if you do the quadratic, you're looking at 1, 2, 3, 4, 5, 6, 7 lines with a lot of numbers. So, I mean, this way requires, you could say, less thought, less knowledge of how to properly do squares and square roots and knowing the distance. But if you do want to do it this way, you can save yourself some time. And that is how we do part B properly. So let me section part B off here. So good job, guys.